Hi everyone, this is the sixth video on how to use genetic algorithms with Abaqus and Python. The idea behind this video is to combine all the videos that we've done so far that coded each one of the steps of the genetic algorithms individually, and now we're going to combine them all together so then we can create this cycle of starting an initial population, evaluate each individual within Abaqus, select each individual, and then make them reproduce and mutate. So then we create a new population, and then we create this cycle for a certain amount of generations until we reach our optimal solution, or let's say near optimal solution. So to start this video, as before, the first thing I'm going to do is to find the function that does this. This is the one I need. And this should be quite a complicated function. So before I even start explaining what this does, I'm just minimizing all of this. So this is what we've done before: initial population, calculate the displacement, which is our fitness function, create the tournament for selection, new population, which takes obviously the tournament and all of that, and then mutation. So now we're going to create the master function that I'm going to clean up first, and then I'm going to explain it in detail. So I'm just going to pause the video and then we continue once I understand better what this does. All right, I had a little bit of time to read through this function. It's definitely the most complicated function to discuss because the one I copied from is actually much more advanced than what I intend for this video. So I had to delete some stuff and make sure I comment some other stuff that we might implement later or might not. So we'll see. Here we have a function called genetic algorithm. It takes the variables that we already defined before. It takes the number of generations that we want to run the code for, which we actually haven't done that. So here I have the population size of 100. Usually you can run this to 25 generations, which I think should be nice for this example. Then we need the population size. So that already we have 100. That sounds good. Elitism size. So this is the number of specimens in each population that goes straight into the next one. I'm going to use 2. So basically the 2 best ones go straight into the next population. And then tournament size. Usually I go with 2 as well. So tournament size is the amount of players that play in a tournament. So the more you choose, the less chance you have for the worst specimens to succeed. So imagine that you're the number 90. Let's say you're the 90th fastest runner, right? The only way you can win the race is if you play against the bottom 10. So you have to choose one of the bottom 10, and then if you win, you have a chance to have your genetic code be transmitted to the next generation. If you put, let's say, 10, it's basically 10 people racing at the same time. If you're the number 90 out of 100, most likely you're not going to win unless you play against number 91, 92, 93, 94. So it's very unlikely that you're going to be the fastest person in that race. So tournament size 2 is what I usually use, but this is up for discussion. Any other number is okay. Just know that the bigger it is, you're decreasing the exploration, so your model will be faster, but you might not reach the optimal solution because you're just converging the math too fast. So I'm happy with this. So that's all I need for this function. So then what happens is the first thing is we start the population binary by creating the initial population. So this we already covered in the previous video. So you're going to get a list of 100 different binaries with the amount of digits that we need. In this case, there will be 44 digits, so 11 per column. So that's what it is. Then I start this process list, which is empty. This is just to keep track of what's going on. I'll show you later what this does. And then I also start this save analysis binary, which is an empty dictionary. And what this does is basically, if a model already ran in Abaqus, I prefer to save the result than to open Abaqus again to run it again in later generations. So if you remember from a few videos ago, when we were testing out how long it took for Abaqus to run a particular model, it took 50 seconds. So you can see here, started at 0641, finished at 0730. So it takes 50 seconds. But if I want to run 100 of them, so that is 5,000 seconds, which is already more than an hour. So just to run one round, it will take more than an hour. If I want to run 25 rounds, so if I times this by 25, we're talking about 34 hours to run the entire thing. So I can speed up the algorithm by fetching the results that I already know, because I'm basically running the same genetic code again. So that's what basically this does. It's an opportunity to save the results somewhere, so then it speeds up the process. Okay, then what is tricky about this is it's not the genetic algorithms that is hard to understand, is the fact that we always have to keep creating folders and jumping from folder to folder to make sure the model doesn't crash. So I have here a function called create folder, which I haven't copied, so I'm just going to copy it from here. So very simple. I'm not going to explain this to you. This I copied from somewhere. I'm pretty sure I copied somewhere from Google. How do you create a folder in Python? So what this basically does, it checks if the folder already exists, and if it doesn't exist, it makes the folder, and most importantly, it changes the work directory to that folder that we just created, which is good, which actually means that I might not need this line of code, but I'm going to keep it just in case. So this is good. So this creates a folder called round something. So let's say I want to run this for 25 generations. The first number we're going to get for I is 0, and then it goes from 0 all the way to 24. So I want to create a folder called round 1. So it's going to be round, and then here is 0 plus 1. So it's going to create a folder called round 1. And then once all of this is done, and it goes back into the beginning, the for loop is going to change it to 2, and then I'm going to create round 2. Then the for loop is going to change it to 3. I'm going to create round 3, so on and so on. Then I create a little print, so I know that the model is running. This is very useful, otherwise you never know if your computer crashed or not. Then we change the directory to this new folder we just created. Then here what we do is we convert the population binary, so the series of ones and zeros, we convert it to the data that we need for our Abaqus model. So if you remember, to calculate our displacements, these variables need to be in decimals. So the chromosome to data just converts binary to decimals. So that's what that does. Let me go back up. So that's what that does. And we're here. And then this is the part where we're going to finally use Abaqus. So for each chromosome in population binary, we're going to print it. So then we have a look about what's going on. And if this is already in save analysis binary, so remember again, this is just to save some computational time. If the results were already run in previous rounds, what this prints is retrieving results from previous analysis, again, just so I can keep track of this. And then it takes the fitness, which is stored in the last value, and appends it to a new variable, and then appends it back to the chromosome where we are, and then change the directory back into the folder that we were. Then if this is not in save analysis binary, so else, then we're going to start a new binary, and this is where we need Abaqus. So we're going to create a folder with a number, with the name of the chromosome, change the directory to that folder, open Abaqus. So this is where the fitness function, which actually has another name in our case, because our case, the fitness function, I gave it a specific name called calculate displacement. So this chromosome 1 should take the variables that we need to create the Abaqus model. So this is the line of code that creates the model in Abaqus, finds the displacement, and stores it in this variable called fitness. And this is done here at the bottom. Let's confirm. Here at the bottom, when I do return max u3, this return command is going to save max u3 in whatever box I say to save it, basically. So that max u3 is going to be saved with this name, fitness. So then we save, now that we run this in Abaqus, we're going to save this into the empty dictionary that we started, so that this all works. Then we append fitness to the chromosome, and then we change the folder back into the original one. Okay, so this is basically the tricky part. As you can see, there's lots of changing folders. We need to be careful about exactly where we are. Then here we go back into the original folder. So this change directory path is precisely the folder that we started with. So it's not any of the rounds. So it's basically the mother folder, if you want to call it like that, or the root folder. Here is just a little bit of genetic algorithm information that is interesting to keep. So here I want to calculate the minimum fitness, and I want to calculate the average fitness. So what I do is I have this minimum fitness as 1 billion or something like that, a very large number. The sum of fitness is 0, and then for each chromosome in population binary, I take the sum and I add the fitness. And as you can see in the next line, this sum is going to be divided by the population size. So basically what I want is the average fitness of a particular generation. And then I want the minimum. So I take the minimum between whatever is the chromosome, whatever is the fitness of the chromosome with this minimum fitness, which is a large number. So then I make sure that the minimum of all of them gets stored. And then I append this to process. So if this back into the beginning, this process is just an empty list. So I want to make sure I keep track of the minimum fitness and of the average fitness for each of the rounds. And that's what I call this process line. And that's basically it. So then the last bit of code is if I is equal to generations minus 1. So basically, if the round is 25 minus 1, and again, this is just because Python starts with 0. So if the I is 24, that means I got to the end of my genetic algorithms. I want to go continue, do nothing. If not, I want to start a new population with the same variables. I start a new population, call it population binary, and basically this over here starts all over again. This for loop starts all over again, okay? So I just need to make sure I update the population, and then I'm going to run this over and over again. And that's kind of it. There's a few print datas that I'm going to show it to you later, but I think this is ready to be tested, hopefully. So what I'm going to do is I'm going to copy the genetic algorithm code down here, and if this runs first try, then I'm just lucky. Most likely there will be errors. So let's see what we get. So genetic algorithms, variables, generations, population size, evitism size, tournament size, all of this is ready to be run. The only thing I'm going to do is I'm going to change the population size to 10, and I'm going to change the generations to 5. So then I don't have to wait that much for this to run. Okay, I'm happy with this, and let's see what are the errors that we get. So I'm going to go here on Abaqus, run the script, and here on my desktop, GA video, this is my GA script, and let's give it a spin. So as I said, I find it very unlikely that this runs first try. There's always some debugging that needs to be done. Okay, so the first thing that needs to be done is actually very simple, because throughout this time that I've been recording, OneDrive kicked in, so now the folder has a different name actually. So let me just copy this. I'm just copying the folder name and updating it here. So basically now this is within the OneDrive of my university. Okay, so that was easy. Let's start again. Okay, so this is good. All right. So I'm going to check these errors in a second, but okay, as you can see, there is something being printed. So we have round 1, we have this first binary that got converted into those positions, which is great. Then new binary, a new model database has been created. Yeah, okay, so the model was about to start. So let's have a look about what's happening. So I'm going to go into line 134, start understanding that. Okay, so column coordinates just has a different name now. Okay, so I think I'm going to change this name here to column coordinates, because variables is the variables of the genetic algorithm, while the coordinates of the columns, that's what I want to go into this function. So then I need to see where this function gets called, which is here, and making sure then this chromosome 1 is the one that gets fed in. So this should work now, because if you can see, what's in position 1 of chromosome is precisely this list here. So this string is in position 0. So let me get rid of this. This is in position 0, that's the binary, and this is in position 1. And that's exactly what I want to feed in as column coordinates. So I'm happy. Let's give it a shot. Okay, as you can see, round 1 got created there. So I know there's a little trick I created in the past. So let me go and find this here. So here I have this function that, as far as I remember, this deletes all the rounds, so then I can start again. Otherwise, I have to go here into the folder and delete that round 1, which, takes time. So we can debug this faster. This basically deletes every folder that starts with the word round. That's basically what this does. So I'm happy with that. And then I need to run this as well into this path. Hopefully I don't crash anything. And by the way, this type of codes, guys, I didn't write this. I just went into Google and typed, how do you delete folders that start with a given word? And then you're going to find in Stack Overflow this type of scripts. So I'm not a coding genius. I hope you guys understand that. A lot of coding, especially in the beginning, is just copy paste it and test it. And that's what you have to do, is copy paste, make sure it does what you intend to do, and you're ready to go. So, okay, I think this is what it does. Let's run it again. Global name shuttle is not defined. Okay, that's easy to fix. Go all the way to the top and import shuttle, and we save and we run again. So now I'm having problems in line 136. Yeah, something's not perfect here. I think in the process of copy pasting, I changed the formatting that I had for this variable. So if I go back here, what I want column coordinates to be is an empty list that then gets the two coordinates within the same list, which is not what I have here. If you see here, I have one big list with all the coordinates in a row. So I want this to be formatted differently. Now, I'm tempted to do a little hack just for this to work, because what's trying to do here is position 0, then position 1. Yeah, and this might create problems all across the model, although it shouldn't be too hard to fix. Yeah, but I feel I'm going to just create a hack so I don't have to change this. So I'm going to keep this as it is. And what I want to do is, here into genetic algorithms, when I go and calculate this placement, I want to change the format of this chromosome 1. So where does this get appended? So this is appended here, chromosome to data, and this is appended to population binary J, and this is where, okay, so I think if I change this chromosome to data function, I should be very happy. Okay, so this is good. So my var data is an empty list, then I append this var decimal. Yeah, so this is going to be a bit silly, but off we go. How can I do this faster? Yeah, I'm going to create a little hack here, which is definitely not the best way to do this. But since I'm recording, I'm going to allow it. So I'm going to go here and I'm going to say if call data. So if the length of the call data equals 2, I want to append to var data. Yeah, I want to append to var data the call data. Okay, so what I want to do then is the var data starts empty, the column data starts empty. And then for the first number, I'm going to append to column data, which is great. And then I'm going to check if the length of the column data is equal to 2, which shouldn't be. It should be equal to 1. But then when I run it again, the length should be equal to 2. And what I want is to append this column data that now has 2 numbers inside into var data. And once I do this, I want to reset the call data to empty. So it was a little hack, but I'm pretty sure this will work. And I'm pretty sure there's other ways to do this, to reshape the size of a list from 8 by 1 to a 2 by 4. I'm pretty sure there are more elegant ways to do this. And again, as when you code something, just make sure you go on Google, and when you're not happy with the solution, just learn new ways to do it. But I'm happy with this solution, so I'm going to try it again. Okay, see what it is now? Now the column data is in pairs, which is precisely what I need. And now that's why this is running. So fantastic, I'm generating something, which is great. Now I can actually go into my GA video folder, and here I have my round 1, and my round 1 is now calculating this crazy. The folder name is a bit large, we can admit that, but now this is looking nice. So now Abaqus is doing its thing, so I hope. So as you can see, this is running with the positions of the columns in these 4 positions, which is great. So it is looking pretty good, if you ask me. Now, one of the things I'm afraid of is that what happens when 2 columns land on top of each other. I wonder if that's going to create a problem, but I'm pretty sure throughout the run this will happen, and then I'll find out what to do in that situation. So this is looking good. I'm just going to pause the video and we'll see you in a bit. Okay, so we're now back, and this actually ran without any mistakes. But as you can see, all the prints that we did are all here. We're going to have a look at them in a little bit. Also, we have here the folders with round 1 to round 5, which, if you remember, I did change the number of generations to 5. Here we go, so that makes sense. And hopefully in each one of them, you should find 10 models. No, actually, that's not true. So on round 1, we do find 10 models. But once we go to round 2, we only find 5. So if you can see on round 1, all the models are new. These were the 2 that we ran that had problems. Okay, so it started here. So that's 1, that's 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's fine. Then when we go to round 2, the first 2 makes sense that Abaqus is not running. It's retrieving results from previous analysis because the first 2 are the 2 that get straight into the next population because of this elitism size. So that's nice. Then we have a few more that ran. Then there's 3 more that we went for from the save analysis and got the results from there. So, okay, I guess this is not too bad. Indeed, a lot of models are being retrieved, and as you can see, this is converging very fast. Now, one of the problems with this thing is I commented all those print results. When we get to round 5, actually the folder is empty. It didn't run anything. So the entire population converges to a simple, to one of these solutions, and then it just says, oh, we're done, we found the optimum. So, okay, for a test, this wasn't too bad. But now what I actually want to do next, I want to be able to see more data. So one of the things I want to do is these print data functions, which I forgot what they do, but I'm going to find them here. Again, this is not too complicated of function. It has nothing to do with Abaqus. It's just something that, again, you can find on Google. So what I want for print data, it chooses a folder, chooses a file name, chooses a title, and then chooses the data. Okay, so prints data. Not sure what the title is though. Yeah, maybe the title from the data. Okay, I see. Then for print final data, this brings also some dictionary. So this must have something to do with the dictionary we start with. Okay, so I'm gonna trust this a little bit for now, and then we'll see. So after the process, this prints data, saves the process somewhere, a file which should be useful. This saves a population binary as well, which should be useful. This weight, I'm pretty sure, is going to create problems. So I'm going to delete this because this is from another example. And then this print final data should save something on the rounds for all individuals. So I'm not really sure what this does, but I'm going to trust that this is going to work. Minimum fitness, average fitness. So that's why this thing I calculated, I actually wasn't using it for anything. So I'm just going to run this one more time. I'm actually going to delete all this mess here. I don't think I need any of this anymore. So done. So I activated this print data, and I'm assuming this is just going to save some data in text files for us to have a look. So I'm just going to go and run it one more time. Hopefully we'll delete those 5. Oh, nope. The process cannot access the file because it's being used by other. Okay, so that's fine. Right, all these output databases are open. Right, this might use a lot of memory actually. Yeah, I need to learn how to close this ODB. I thought I was doing that. So I'm pretty sure to close the ODB, it's just odb.close. So I'm going to do that like this. And hopefully that doesn't keep all those ODBs in memory. That's probably why this takes a little bit longer to run. So I'm see if this goes now. Yep, okay. So I'm going to pause the video again, see if we can use a little bit more information on what's going on now. Okay, so now the genetic algorithm completed another run. So this looks, again, like the last round is just previous analysis. So clearly this is converging a bit too fast, I would say. Maybe it's just because there's just 10 in the initial population, who knows? But still more tests need to be done for me to be happy with the solution. But I'm happy that it is running. And now if I go here on round 1, I should be able to find these 3 text files. So if I open this process 1, yeah, Notepad is fine. So here we can see for round 1, the minimum fitness was 60. And remember that the fitness is the displacement. And then the average was 199. So that's interesting. If I go to population binary, so this last number here, 60, is the fitness. So as you can see, this is the genetic code in binary, then this is the variables, and then the fitness at the end. So this got 60, this got 169, 127, 82. This got actually 1 meter displacement. So this is, I know that's not true here. This got 113. So 298 is the worst. No, actually 598 has got almost more than half a meter displacement. So there are some bad ones. You can see the average 200 is not too bad, and indeed minimum is the 60. So what I expect to do is that if the selection is working fine, this is my best one. So I should, when I go to round 2, I should be able to find the same one right at the top. And here it is. So indeed with 60, I can just paste it. So that's indeed the best one. And the 82 as well got transferred. And then as you can see, there's a lot of them with 82. So clearly, this is converging way too fast, but I'm very happy that this is working. That's the part that matters. So if I go now to the last one, round 5, I should be able to find that all individuals that then should have all the ones that got calculated and find which ones were the best. So as you can see, this round gives me the round where they were calculated. And now how can I find the best one? It's not in order, but I guess the best one is this one with 57, which was found in round 3. Yeah, that seems about right. So I'm generally very happy with this. So if I go to population binary, I'm assuming that all of them will be that one with 57. Yeah, here it goes. No, there's a few with 60. So as actually, there is a little bit of improvement still to be made. So if we go now to the process, and this is good, you'd never want the minimum and the average to be the same, because that means the population just got uniform. Basically, all of them got the same solution. So I'm very happy with this. I'm going to terminate the video here because this was just a test, and in the next video we're going to be running this with the proper number. So what I'm actually going to do is actually increase this to 100, increase this to 25, and let it run. And then the next video will start from here. Another thing you need to see is, because we have 4 columns and this is the X range is with 6 binaries and Y range with 5 binaries. In total, we have 44 digits, so binary digits, which gives you 2 to the power of 44 different possibilities, okay? Which, if you put this in a calculator, 2 to the power of 44 is 1.8 times 10 to the power of 13. So 1.8 with 13 zeros after. So it would take forever to test every single one of these possibilities, okay? And you'll see with genetic algorithms, maybe with 1,000, maybe with 2,000, we'll be able to find the optimum without having to test all these crazy ones. At least that's the idea. So I'm going to terminate the video here. I'm going to delete this. I'm going to terminate the video here, and we'll continue in the next one. So thanks for watching and have a nice day.